Ma'am, Vimla Devi, ma'am. Mm.
Hello, Dr. Meghala, am I audible?
Ma'am, am I audible, ma'am?
Yes, you are audible, ma'am. Am I audible to
Yeah,
you?
thank you, ma'am. Yes, ma'am. We'll start the session by 11, ma'am.
Okay. Are we waiting for someone
Thank
to
you,
join?
ma'am. Yes, ma'am.
Okay.
Thank you. Am I audible?
Am I audible? Happy morning to one and all present here. I am Deepa, coordinator of this FDP. It's my great pleasure to welcome our resource person, Dr. M. Vimala Devi, Assistant Professor, Department of Computational Intelligence, SRM College of Engineering and Technology, Chennai. Welcome you, ma'am. I feel honored to welcome all the participants for taking a keen part on this FDP. Welcome, professors. I'm sure that you all will feel enriched with knowledge after completion of this FDP. Once again, welcome you all. Thank you.
It's my immense pleasure to welcome today's speaker, and let me introduce today's speaker, Dr. M. Vimla Devi. She's currently working as Assistant Professor in Department of Computational Intelligence in SRMIST, Katangruthu. She has a total years of 17 years of experience in working in both industry and academics. She played the role of technical lead and project leader in developing projects in IT sectors. She received doctorate degree from Pondicherry University in software engineering. Her research interests include software engineering, machine learning, and deep learning. Dr. M. Vimla Devi is NVIDIA recognized university branch ambassador for NVIDIA Fundamentals of Deep Learning course. And it's my immense pleasure to welcome Dr. M. Vimla Devi and I hand over the session to our resource person.
Thank you, Dr. Meghala. Hope I am audible to everyone.
Yeah, ma'am, you're audible, ma'am.
Okay, so is my video available? Able to see me? One second.
Ma'am, video is not clear, ma'am.
Yeah, one second. I'm just adjusting the sound. Yeah. So I think I'm visible. Fine. So very good morning to one and all joined here for this session. So I thank Dr. Meghala for inviting me for this session and for giving me a very nice introduction about me. So shall we move on? Shall we start? So it's already 11:02.
Yes, ma'am. Yes, ma'am.
Yeah. Thank you. So I feel also happy to be here since I'm an alumni of this institute. So that is the one of the reason, and I feel so happy to present today's session. So let me share my screen. So I just let me just confirm whether my screen is visible. Okay, is my screen visible to all?
Yes, ma'am.
Okay, thank you.
Yes, ma'am, visible.
Thank you. Thanks for confirmation. Before I begin, Dr. Meghala, so I just wanted to know about the participants of today's session. So is the participants the faculty of the SMVC Institute or who are the participants?
Ma'am, the faculties belong to all of the colleges. We have 182 participants from different colleges and we also have international participants, ma'am.
Okay, good. Okay, so fine. So let me start. So in today's lecture, so we will be seeing about the introduction to deep learning, and we will be touching about the concepts of the deep learning and how the learning is happening and how the network is structured, and we'll also look something about what is a convolutional neural network, and I also have some samples that I'll be sharing with you people. So how to develop a neural network and how a convolution neural network can be developed. And we have some sample data sets which we will be applying to those models. And we'll study how to analyze and the accuracy of those models. Fine. So this is the agenda for today's presentation for the next 1 hour. So we'll start with an introduction to deep learning and how the training basically happens in a neural network. followed by the concepts of convolutional neural network and how a convolutional neural network can be implemented. We'll see those with some example. And I'll also be touching upon what is meant by pre-trained model and what are the pre-trained models that are available to us. Okay. So we are into the first part of the agenda. So before I start this presentation, I have taken most of the contents for my presentation from the NVIDIA GLI, that is Deep Learning Institute. As Mehala has pointed out, I'm the brand ambassador for this NVIDIA University Ambassadorship Program for the fundamentals of deep learning. So I just wanted to share the credits to NVIDIA for this contents and so on. Okay. Fine. So we all would have got enough introduction about what is meant by artificial intelligence and where it has all started and where we are right now, right? So without spending much of time, so in order to establish a connection, about from the to the topics whatever I'm planning to deliver today. So I just start with this introduction about artificial intelligence. So we know that when the computers were introduced, our ultimate aim was to simplify the tasks of humans, and we wanted to bring the computers to the near intelligence capability of a human. So that is where we all started with. And initially we thought we could make computers behave similar to human, but that problem seems to be a harder thing at that particular time because of certain constraints. But right now we are seeing more improvements, and we are nearing the intelligence level of a human. So this is what the scenario which was during the beginning of the computers and the artificial intelligence and so on. Coming to the design of a neural network, we all know the neural networks are inspired by the concepts from biology, how our the brain and the neurons are interconnected and how it works. Even though this neural network concepts started in early 1950s, when we were not able to successfully utilize or see the capability of the neural network, as I said, because of certain constraints that are available at that time. So these neural networks were outclassed by the Van Neumann architecture, which we have right now. So during those periods, we were developing something called as an expert system. So an expert system is we will be having some rules, and the programmer will be coding these rules. The rules are the complex in nature. There are so many levels of if, then, and construct like that. And the programmer will be coding these if, then rules to the computer. Okay, and the computer will categorize based on the rules that are input by the programmer. So the limitations of those expert systems are as the programmer feeds the the rules. So the expert system's performance is limited to that. So this is a scenario wherein in the picture or in the slide you see around 3 pictures, right? So what do you see in these 3 pictures? Can I get some response? We have 3 set of pictures. What are you able to see? The first picture, the middle one, and the last one. Can I get some response? What is the first picture?
Ma'am, we have muted the participants, ma'am.
Oh, okay, fine. Okay, then in that case, it will be hard for me to read the chat also now. It's okay, no problem. Let me continue. So when we, show these pictures, to different humans, they say they see an ocean, and they see a cat, and they see, a garden or a daisies and some grasses, and they say a vintage car, an yellow car, and so on, right? So the perception, the perception of the humans, how they see things, is different. But how to make the computer to recognize these kinds of images is a challenging task, right? So what I'm trying to say here is, if a system can be expressed by a rules, well and good, right? So we can program the computer to do that. But the rules are much more complex like this, right? So how to frame rules to identify the images in these pictures, right? So these are some of the complex tasks. So this is where the limitations of this expert system come in. So basically, our artificial intelligence or the machine learning and deep learning models rely on the concepts how the children learn, right? So how the children learn, right? So we just expose our children with different forms of data. We give them, feed them with a lot of data. Say, for example, if a child is learning to recognize an apple, we show this is an apple and this is a mango, but means that this is not an apple. So an apple will be in this particular shape, will be in this particular color, will be in this particular size, right? So we feed, the children with a lot of data and we give them correct answers, right? So this is an apple and this is not an apple. And during the course of the time, the child, learns by itself. Okay, so whenever it recognizes an apple in the future, it recognizes correctly that it is an apple, depending upon its previous exposure to those kinds of data. So it has picked up the patterns that are available in an object, so the child is able to recognize it. So this is the basic concept behind this learning, deep learning and machine learning models operate on. So as we say, at present, we were able to, utilize these deep learning concepts to solve some of our real world problems. This is possible now, right? But this is not possible some 20 to 30 years back. So why this is possible now? Because of two things. One is the abundance of data, right? So we have a lot of data available now, so that we can feed our model with n number of data. So the model exposes itself to different types of data. So the learning capability of the model improves. So as an advent of this digital era, the internet is supplying us with a lot of data. So with this lot of data, we were able to make our model learn and we were able to use our models efficiently. And the next thing is the abundance or availability of our computing power, right? So whenever our brain processes an information, so within how many seconds it is processing, how many frames per second it is processing, right? So with that particular, to match that particular capability of our brain, we need a lot of computing power. So with these two things, that is the data which is abundant now and the computing power which is also available to us now, so we were able to see, the benefits of artificial intelligence and deep learning, which are booming now. So that is, what we are trying to say here is, even though these concepts are started in, early 1950s, it is gaining, momentum now because of these two things. One is the availability of the data and the other availability of the computing power. Okay. So let's move on to see about how a traditional programming is different from neural network classifier and so on. So how do we build a classifier in a traditional program, right? So in a traditional programming, first we have to identify what are the rules to classify. Okay, so what are the rules? Say for example, if an apple has to be classified, so what are the rules defining that as an apple? The size, the color, and the shape, and so on, right? So these are set of rules. So we have to identify and define those set of rules and program these rules into the computer and feed the program with examples, and the classifier will classify whether it is an apple and it is not an apple. So this is a traditional way of programming. So what is an machine learning approach to the same classifier problem, right? So in a classifier problem, we don't program the rules to our computer, the computing software, whatever we are applying. We just show the model with some samples. Okay, the model itself is going to learn and frame the rules on its own, and it is going to categorize. That is the difference, okay, between our traditional way of building a classifier and a machine learning way of building a classifier. So when to choose a traditional or a classical way of programming, and when to go for deep learning, right? So if the rules are clear and it is straightforward and there is no inherent complexity which is available, we can go for classical programming. Whereas if the rules are very complex or nuanced and difficult to program in a computer, we go on for a deep learning model. So with respect to the previous pictures which we have seen, right? So it is very hard to derive the rules that correctly classifies those pictures. So in those cases, we can go for deep learning. Okay, so these are the scenarios in which we take a decision when to go for a classical programming and a deep learning program. And the next 3 slides are going to tell you what is the applications and where all this, the AI, ML and DL models are being applied. So we have all seen, the applications in computer vision, the robotics, and in various object detection techniques, and also recently in the self-driving cars. And with respect to the, the natural language processing, it is, very well used in the real-time translation, voice recognition, and also in virtual assistants. We people are already using it, right? And also in the recommendation system. So the advertisements and then the shopping recommendations like your Amazon or eBay and you use, you know, a Spotify app or something, right? So we have already seen, you know, some recommendations coming for us. So these are the applications of your deep learning or machine learning models. And also in reinforcement learning, we have already seen, you know, the bots, you know, which are beating the world champions, like in the AlphaGo games, and you know, the professional video gamers. So they are also beat, you know, by this bots, you know, which work on the principle of reinforcement learning. So what the reinforcement learning is like, you know, whenever an agent, we call an, you know, a robot, we can call a robot as an agent. So if an agent is taking a particular action, right? So the environment is going to reward, you know, that particular action based upon the goodness of the action, right? So by depending upon the reward, you know, the agent is going to learn how well it can take the actions in the future, right? So that is what is all about that reinforcement learning. So these are some of the applications, you know, which we people use in our day-to-day, you know, systems. So in this, you know, what are the softwares, you know, that are most predominantly used for this, you know, deep learning models are, you know, the TensorFlows and Keras, which are provided by Google, and PyTorch, which is provided by Facebook, and MXNet, you know, the Apache's MXNet. So these are some of the popularly, you know, used frameworks, you know, platforms which we can use for developing a deep learning model, right? So in these, in some of the samples which I'm going to show today, so I'll be using, you know, this Keras, TensorFlow and Keras, and so you know, we just request, you know, the researchers and the developers to explore, you know, other platforms which is also available. So with this brief introduction about what is meant by an artificial intelligence and machine learning model, so we will move on to our next part of the agenda. So we will see how a neural network works and how a neuron is, you know, what is the importance of a neuron in a network. And we'll also see what is meant by an activation function and the concepts of, you know, overfitting, and how these neurons and neural networks can be used for the, you know, for the problem of classification, right? So am I still audible and connected? Is it good to go? Is there any message? Dr.
Yes,
Meghna?
ma'am.
Yeah. Okay.
Yes, ma'am. Yes, ma'am.
Yeah, thank you. Thanks for the confirmation. Fine. So now let's look at a simpler model. So in the screen, we have a model, an equation of a straight line. So we are all familiar with this model, y is equal to mx plus b, right? So here we wanted to build a model, so which is going to predict a straight line that is going to pass these 2 points, okay? So here we have an input x, okay? So followed by the output value y, okay? So these are the inputs, and we wanted to find the optimal value of m and b, so that we can fit a straight line that is passing through these 2 points, okay? So we want our, you know, machine learning model to learn and find out a straight line to fit this. So this is the problem. So we know this m is the slope and b is the y-intercept, right? So how, you know, this is a toy example which we have taken here. So even though we know, you know, other, you know, solutions which can solve this particular problem, but we are trying to provide an artificial based solution in order to find a straight line that is going to fit this particular model, okay? So this is what we want, right? So we wanted to find a straight line like this. So how do we fit that? So we just start random, right? So in artificial intelligence, we wanted to find an optimal value of the variable so that the predicted value and the actual value are almost the same, okay? So we wanted to minimize the error in the predicted values, you know, when compared to the actual value. So in our, you know, this toy example, we assign some random values for m and b, and then we try to analyze the what is, you know, the accuracy of the model, or we wanted to measure the loss in the sense the difference between the predicted and the actual. So we wanted to minimize that. So for that we use, you know, the something called as a loss function, so which is nothing but a mean squared error value, which we wanted to minimize, right? So in this particular table, which you see here in the left, so we have an x value and y value. Y value is the actual value and y cap is the predicted value, okay? And the error function is calculated by using this particular formula. So in this example, it's a regression problem, and we have taken an error function to be the mean squared error. So the mean squared error is going to compute, you know, the difference between the predicted and the actual, the square root, and it is going to average it over the sum of the samples that we have taken, right? So considering this particular equation, so our predicted value is 4 for the value of m and b, which we have chosen. So m is -1 and b is 5, which we have chosen randomly, okay? So during the course of this learning, we wanted to change these values of b and m so that, this the error value is minimum. So we want the error value to be nullified. That is our ultimate aim. So when we start with this particular random value, we just calculate this MSE value. So the root mean square error is also one of the function. When we take the root of this MSE, it becomes our RMSE. Okay. So this RMSE value for this particular sample, which we have taken, is around 2.5. Okay. So this is the line for the value of m and b, which we have taken to be -1 and 5. Okay. So we just measure the error. Okay. So here our error is still high, which we wanted to reduce. So in the next iteration, we try to change the value of this particular m and b so that the error gets minimized. Okay. The process continues like that, and still we achieve a 0 or we achieve a maximum, the minimum value, whichever in the maximum iteration that we are performing this particular task. Okay. So that is what a simpler model and any machine learning model will have on its own, right? So this is an equivalent code with respect to the calculation of this the RMSE value. So here in this particular slide, for the same toy example which we have seen, this is nothing but the surface plot, right? So in a surface plot which you are able to see, it is a curve, and we wanted to find out what is the minimum, the global minimum. So the global minima is where our RMSE value is minimum, right? So in the corresponding right, you have a contour plot of the surface, the surface plot, which is given on the left. Okay, so because it is easy to visualize, right? So for the initial value of m and b, that is -1 and 5 respectively, which we have chosen. So we are here. Okay, so at this point, this is our loss, and we are here in this particular location. Our ultimate aim is what? We wanted to land up in a location where this loss is minimum. So as a human, we are able to see from this particular plot, this is our target location. Okay. So we want our machine learning model to move or converge from this current location to this target location. Okay. So this is what, the process which we call as the learning process. Okay. So what we do next is we adjust, the value of b to be 4 instead of 5. So the line, now the fit of the line is here. Okay. Still we have some error function. So we then move this value of m. Okay. Then we keep on moving like this, right? And ultimately we land up in this particular target location where the loss is minimum, right? So this is how the learning happens in any machine learning model. Okay. So in order to achieve this, we have, some terminologies which is defined over here, called as the gradient, the learning rate, the epoch, and the batch and the step. What is a gradient is? The gradient is nothing but will tell you in which direction the loss decreases. Okay. So we wanted to move towards that particular direction. Okay. And the learning rate will tell you how far, we can travel. Say, for example, we are in this particular, location. Okay. Okay. If we are in this particular location, so we are still so far from the actual target. So we can fix a larger learning rate. But once we, keep moving on to this particular point, we have to reduce our, the learning rate so that we don't want to miss our target location. Okay. So the learning rate will tell you how far we have to travel from the current location. Okay. And the epoch is nothing but the terminology, which defines a model update, whenever you are using a full data set. And batch is nothing but from the entire data set, we just take some samples and then we do this particular process of iteration. Okay. And the step is nothing but an update to the weight parameter. So we wanted to update our weight. So we wanted to learn what are the optimal values, for that particular weights. Okay. So once we have arrived at the optimal values for that weight, we can use that particular model for the future prediction. Okay. So this is how, any machine learning, model works. And we have, optimizers which help us, in order to find this particular, the gradient value. Okay, so the gradient value, so that, which we can be used in the back propagation to learn our, weight parameters. So these are some of the popular optimizers which is available. Okay, like your ADAM, ADAGRAD, RMS prop, and SDG, and so on. Okay, this SDG is stochastic gradient descent. Okay, so what is an loss function with momentum is, so if you imagine there is a ball rolling down a hill like this, right? So a ball may land up in this particular location. So this we call as a local minima, right? So our ultimate aim is what? In order to land in the global minima. So we wanted to skip this particular local minimum. So we just adding a particular element of momentum to this bar, so that we just skip, being trapped into the local minimum. Okay, so this is what is called by an optimizers, with momentum. Okay, so these are some of the popular optimizers which is available. Okay, so next we will talk about something called as an activation function. Okay, so in machine learning model, there are three categories of activation function. So one is a binary step function, the other one is a linear activation function, the third one is a non-linear activation function. So what is a binary step function is, it depends upon the value. It operates based on value of a threshold. Say for example, you pass an input. If the input is exceeding the threshold, then the neuron will fire. Otherwise not. Okay, so that is called as a step function. Whereas in a linear activation function, you can see the curve is linear. So we cannot introduce any non-linearity in this particular linear activation function. So whenever we introduce non-linearity, only then we can use that particular function in back propagation. Okay. So that is what is about linear activation function. So here in this slide, you are seeing some activation functions called as ReLU and sigmoid, right? So these ReLU and sigmoid are non-linear activation functions, whereas in the left side you are able to see something which is a linear activation function. Okay, so in ReLU, as you can see in the graph, okay, so only for the positive input values the neuron fires. Okay, for the negative values, and it is still zero, that the output of the neuron will be zero. Whereas in sigmoid, you can see the value ranges from 0 to 1. Okay, and there are also other non-linear activation functions like your tan h, where it ranges from -1 to 1, and there are also some more variations of this ReLU, like your leaky ReLU and parametric ReLU and so on. Okay, so what is a leaky ReLU is, as you can see in this particular ReLU, for all the negative values, the neuron will not fire. The neuron will always output 0. In order to avoid this particular dead neuron, so we just go for leaky ReLU. In leaky ReLU, even for some negative values, the neuron will output some values. Okay, so that is what the concept of leaky ReLU. But these are the popular non-linear activation functions like your ReLU and sigmoid and tan h and so on. Okay, so this is the plot of the activation functions. Okay. So next we'll discuss about the concept of overfitting. Okay, so what our ultimate aim is, as you have seen in the the previous a model, which is a simpler model, the toy example which we have seen. Our aim was fitting a straight line to the points so that we can predict in the future the prediction point will lie on the straight line, right? So this is in this particular example, on the slide which you are seeing, there is a model, and one model is on the left and the other one is on the right. So which you see, which you feel a better model, right? So I just pause here for a moment and I want the participants to think, which model is better, whether the left one or the right one. Because in the left one, you can see the error is 0, right? Whereas in the right one, the MASC is not 0, but it is a higher value when compared to the left one. Okay, so which one is better, right? So our ultimate aim is what? We wanted to minimize that. So in that case, this might seem better because we were able to fit almost all the data points in that particular model. Okay, whereas this this is not, seems to be a better fit, right? But for this particular sample, now if I increase the samples to this, right? So if I calculate the error function, so the error MSE is greater for this particular model, whereas it is lesser for this particular model. Okay, so this is an example wherein this model has been overfit. Okay, so overfitting whenever overfitting happens, it means that the model has memorized the data points. Okay, so the model has memorized, and for the newer data models, the newer data points, the model will not be able to perform better. Okay, So it will be, during the training, the accuracy will be very high, whereas in the testing, the accuracy will be very less. So that is the symptom of overfitting. Correct? I just repeated. So whenever the accuracy is very high for training, and when the accuracy is less when compared to training, right? So that is the symptom that your model is overfitting. Okay, so this is an example of overfitting. So considering this particular scenario, so the answer to the question is, this is, the model which is better when compared to the left one, because the left model is overfitted. Okay. So what is meant by training and validation? So whenever we are training our neural network, okay, we just feed our, network or model with some data. Okay, so we split our model data set into training data and validation data. Okay, so normally we split in the range of 80-20 or 70-30 or so on. Okay, so the training data is it is a labeled data which will be given to the model, and the model will be able to learn and try to make prediction, and it will try to reduce the error. Okay, so once the model has completed training, then we validate our model using the validation data. Okay, the validation data is not seen by the model during the training process. Okay, so once we validate this model using the validation data, we will be able to measure how well our model is performing. Okay, so what is overfitting? As we have discussed in the previous few slides, whenever the model performs well on training data but not on the validation data, then it is an evidence of overfitting, and because the model has memorized. Okay, so ideally the accuracy or the loss should be similar between the training and the validation data to avoid this particular overfitting. Okay, so this is a scenario, an example of an overfitted model. As you can see here, the black, the line, which tells, that the model is overfitted. Okay, fine. So from we have seen how the regression model happens, right? So with the examples which we have taken so far, we just go on with the sample. The first exercise we will take in this particular session, we are going to take a data set, which is nothing but an American Sign Language data set. Okay, so we have around 26 alphabets in English. Okay, and we are going to take 24, alphabets, because two of the alphabets, that is J and Z, require some movements. So we cannot, use that particular, use those two classes for our, sample. So remaining, we have 24 classes. Okay, so 24 classes in the sense, we wanted to show our model the image, the pictures like this, and we wanted our model to classify whether it is an A or B or C and so on, right? So is the problem clear? This is nothing but an American Sign Language, problem. So this is, say, for example, I just feed the model with this particular image. Okay, so the model will tell me, okay, so this image belongs to F. So these are the classes, right? A, B, C, D are different classes. So we have taken around 24 different classes for this particular example. Okay, so let's move on. I'll just show. Okay. I'm just opening my Collab notebook. Okay. So this is, the notebook, which is, classifying the American Sign Language data set. So I'll just explain how this particular, program works. Is my screen visible to all?
Yes, ma'am.
Okay, thank you. Okay. So as we have seen here, the American Sign Language, data set contains 26 letters, right? And these two letters, J and Z, requires movement. So we haven't included in this particular training data set. So the number of classes in our training data set is 24. Okay. So this data set is available in Kaggle. So in this particular example, I'm going to use, the Keras library. Okay. There are some data sets like your MNIST and, Fashion MNIST and, the the housing data set, which is available in Keras, inbuilt in Keras. But this American Sign Language, we have downloaded from the CAD. Okay. So in this example, we will see how to download and load this particular data set into our model. Okay. So as we have told here, we wanted to first download the data set and split the data set into training and validation. Okay. So this training and validation corresponds to this X-train, Y-train, X-valid and Y-valid. Means that X-train contains the images, that is the pictures, and Y-train contains the corresponding labels of these pictures. Okay, so the data set is a labeled data set. Okay, means that the particular image will contain the value, whether it belongs to A or B or C or so on, which class. We have 24 different classes. This is a labeled data set. So we are splitting the data set into training sample and validation sample. X-train will have the images and Y-train will have the corresponding labels of that training data set. And similarly for the validation, X-valid will have the pictures of the validation data and Y-valid will have the labels of the corresponding validation data. Okay, so first we wanted to load the data and split it. Okay, so that is what is being done. So we are going to make use of pandas library for here. Okay, so this is where we are just reading. So I just stored my data in my Google Drive. So I'm just mounting the drive and I'm just reading the data. That's what happens in this particular cell number 3. Okay, so we are just reading the training data and validation data, which is available in a CSV file. And if we look at the data set, okay, so we are having around 784. Okay, means that 784 pixels. The pixel, this image is 28 cross 28. The size of this image is 28 cross 28. So that we have around 784 pixels. Okay, so that is what is being given over here. So the value of each and every pixel will range from 0 to 255. Okay, so this is what, are you able to understand how this the data is being designed? So we have the size of the images 28 cross 28. So each and every that is 28 cross 28 number of pixels. So totally we have around 784 pixels, and each and every pixel range value will range from 0 to 256. That is why we have this particular value. So we are just splitting here, extracting the labels for the training data and the validation data, and then we are assigning here in this Y train and Y valid. So this is for validation and this is for the images. So as you can see here, we have totally around 755 image, and each image with 784 pixels. So if I see the shape of the X-train is what? X-train is nothing but the training data. So we have around 27455 training data, and then 7172 validation data. Okay, so are you able to understand what is this? So this 27455 is nothing but the number of training samples, and 7172 is nothing but the number of validation samples, and the size is the same. So size is named as 28 cross 28 image. Okay, so that is why the size is 708. Okay, fine. Now let's visualize how our image looks like. See here. So these are the corresponding labels. Okay, so which is numbered from 0 to 24. And these are the corresponding images. The images is 28 cross 28 pixel, and these labels at the top you are able to see here. Okay, so we have just printed around 20 sample images. Okay, so we want our model to train using these images and correctly classify to which class it belongs to. That is the problem. Okay, once the data is loaded and we have split that into training and validation, our next step is to normalize the data. Okay. So as you can see here in this particular example, the each and every pixel value ranges from 0 to 255. That is 256 values. So we wanted to normalize that. So we wanted to normalize it so that the value ranges from 0 to 1. Okay. So next step is normalization. Okay. So if you see in the X-train, the minimum is 0 and the maximum value is 256. So in order to normalize, this has been done in this particular cell. Okay, so here we are normalizing the data. Okay, and the next one we are using something called as the the categorical encoding. Okay, say for in this particular example, we told that there are about 24 classes, right? One is for A, B, C, and C, and so on. So we have multiple classes like this, 24 different categories like this. So in this example, we have to categorically encode this particular labels, so that we are using the call to the API, the function to categorical, which is available in the keras. Okay, so you can go to keras library and see how this the to categorical value works. Okay, so we wanted to categorically assign the number of classes, so that is why we are just using this to categorical value. The number of classes is 24. Okay, so once these steps are done, then our next step is to build a model. Okay, so here we are building a normal neural network. Okay, so it is not a deep learning model. It is a normal neural network where we have only 3 layers. Okay, so see here again I'm using this keras model, which is a sequential model. There are other models which is available in keras. In this example, I'm using a sequential model. What a sequential model is sequential model will allow me to stack layers, one by one. So here in this example, we have 3 such layers here. Okay, so this dense layer is nothing but a neural network layer, and the number of neurons in this particular layer is 512, and the activation function for this particular layer is ReLU. Okay, and see the input shape of this particular layer. So this is the first layer. And this is your first layer, and this is your second layer, and this is your output, the final layer. Okay, so the first layer I'm going to pass my training samples, and the shape of my training sample is what? 784, right? So this is the pixel size. Okay, so this layer takes the input shape of 784, and this will output the shape which is equivalent to the number of neurons which is present in that layer, which is nothing but 5. That will be passed as an input to the second layer. So the second layer also has a 512 number of neurons. And again, this activation function is a ReLU function here. Okay. Finally, this is my output function, output layer. And the number of classes in my output layer is nothing but 24. So 24 corresponds to the 24 different alphabets. I'm using a softmax activation function here. So softmax is nothing but, whenever we have a multi-class problem, okay, like this in our example, we use a softmax layer at the output. Okay, we usually use the ReLU functions in the hidden layers, whereas in the output layer we use a softmax layer. Okay, so for a multi-class problem. So these are the 3 layers I'm going to have in my neural network model. Okay, so once I created these 3 models, I can just see the summary of the models which I have created. Okay, so I have 3 models, 3 layers. The first layer, second layer, and the final output layer. Okay, then the shape of the this first layer is 512, because this corresponds to the number of neurons, and the shape of the second layer is also 512, which corresponds to the number of neurons in that particular layer. And finally, I have 24 classes, which is nothing but the size of my number of classes in my output layer. Okay. So these, column which you see here, the last column tells you what is the number of parameters. Parameters are nothing but the number of parameters the model has to learn. Okay. So there is something called as a parameter and a hyperparameter. Okay. So I'll tell you what is the difference between a parameter and a hyperparameter. Okay. So the parameter is something the model has to learn on its own. Okay. So those parameters are called as, the parameters in a machine learning. Whereas hyperparameters are something which the model is not learning by itself, but we are setting them. Say for example, the learning rate and the number of clusters. Okay, so these are values which we set. Okay, but we wanted to optimize these hyperparameters, but the model is not going to learn those parameters, right? So that kind of parameters are called as hyperparameters. Whereas a normal parameter in a machine learning model is something which the model is going to learn during the training process. Okay, so these are the number of parameters this particular model has to learn. Okay, so you can see that in a summary when I call model.summary, which is available in keras, it will be able to tell me what are the number of layers which I have created and what is this output shape and what is the number of parameters available in each and every layer. Okay, so once we have defined our model, our next step is to compile the model. Okay, so for compiling, I just call model.compile. So this model is nothing but which we have created here. Okay, so this is our model, right? So we have created a sequential model and we have added these 3 layers to that. And once we saw the summary of that model, and the next one is we just call a compile. okay, method on this model. Okay, so for this compilation, we use this categorical cross entropy because we have categorical value here, the 24 categorical values. So that is why we use categorical entropy. There is also binary cross entropy which you can use if your model is going to classify only 2 classes. Okay, and here we wanted to study the parameter accuracy. Okay, so by passing these values, I just compile it, and then the next step is to train the model. Okay, so for training, I have to pass the training data and the training label. Okay, I just set the epoch to 20, and verbose once means it will output for each and every epoch what is the value. Okay, so see here, and the validation data is passed like this. Okay, so you see here there are the model has executed for around 20 epochs, and these are the training accuracy and this is the validation accuracy. Okay, so as you can see, gradually the training accuracy and validation accuracy has improved. Okay, at the end of 20th epoch, you can see the accuracy is around 97%. Okay, so this is the training accuracy. Training accuracy is 97%, and the validation accuracy is 82%. Okay, so our model is performing well. Okay, so we were able to achieve a validation accuracy of 82. Okay, this is how you just compile. So now your model is ready. Okay, so the model is trained. Okay, so you can use this model to predict by giving any sample image like that. Okay, so this is how you usually build a model. Is that clear? Am I still connected? Is it good to go? Can I get some confirmation, Meghla? Am I audible?
Yes, ma'am. Yes, ma'am. You're audible.
Yeah, thank you. Thank you. So with this, valid accuracies values which we have got, what we infer, right? So we see that training accuracy is high, whereas validation accuracy is less, right? So this is an example of what which we call as overfitting. Okay, so this is a simple neural network model wherein it has performed well, but we were able to see some sort of overfitting here. So this overfitting we can avoid by using which we call as a neural network. So that is where we go to our next part, the third part. Okay, so let me continue from here. So far we have seen about what is a simpler model and how we can build a simple neural network. Okay, and we have also created a model and we have estimated the accuracy, and we were able to see the training accuracy is still higher than the validation accuracy. Okay, so we wanted to still improve our model. So that improvement we can bring in by using CNNs, which we call as convolutional neural network. Okay, so what is meant by a kernel and a convolution? So you have already seen, any image processing software, right? You will be able to blur, sharpen, and brighten, and darken the image, right? So these are some of the features which are possible by using some kernels. So these are kernel. This is a kernel. Kernel is nothing but, in this example, is a 3x3 matrix with some values. So these values are nothing but the weight values. These values are already learned and pre-trained. So once I convolve this particular kernel over this image, right? So I'll be able to blur my image. Okay. So this is a kernel to sharpen the image. So these values are learned and this has been set. So if I convolve this particular kernel over the image, I'll be able to sharpen it. Okay. And this is a kernel for this brightening. So if I convolve this particular kernel over the image, I can brighten it. Similarly, this is the kernel for darkening the particular image. Okay, so this is what is made basically what is meant by a kernel. And convolving means putting the kernel over the image, and I just try to find a weighted sum. Okay, so which we'll see in the next slide. Say for example, I have a blur kernel like this. So this is a 3x3 kernel. This is my original image, which is represented in forms of zeros and ones. Okay, so once I convolve this, I just put this kernel over the original image. Then I just multiply the corresponding values. Then I calculate the final sum. Then I put it here. Okay, so this is what happens in the convolutions and kernels. Then the next step, what I do, I just move to the next set of values. Okay, then I calculate the value, and then I move to next. So like this, I just convolve my kernel over the image. Then finally, I arrive at a convolved image. Okay. So what we are trying to learn here is, we are trying to learn the features that are available in the image. So that is what our ultimate aim. So for that, we are using the kernel. So the kernel is nothing but a matrix. So it can be a 3x3 or 5x5 or whatever it is. So in this example, it is a 3x3 kernel. So the convolution is nothing but the process of convolving this particular kernel over the image, and we are arriving at a convolved image. Okay. Then what is meant by a stride? Okay, so stride is, in how many steps we are moving. So in this first example, you are able to see we are having a stride of 1. So means that one column by one column, we are just moving the kernel over the image. Okay, so that is called stride 1. If it is stride 2, we are, skipping 2 columns at a time. Okay, so whenever I use stride 1, so in my output convolved image, I'll be able to get 4 values for the sample that I have taken. Similarly, if I set a value of stride to 2, I'll be able to get 2 values only, because I cannot move the stride further to the third. Okay, because no columns are available to the right. Okay, I'll be able to get only 2. If I set a value of 3 here, so the first one will be, this particular window, and the next step will be this particular window, so that I'll be getting 2 values only here. Okay, so if you see in this particular example, when I set a value of stride 2, the last column is not being utilized, right? Because we don't have any more further columns to the right, so that I can move my kernel, right? So there is a loss in the data. So to avoid that, we have something called as padding. Okay, so padding is nothing but we are, around my original image. I hope this is the same original image which you are able to see a heart in between, right? So I'm just using a concept called padding. So there are 2 types of padding. One is one can be a zero padding or mirror padding. So zero padding will look something like this. And this is an example of mirror padding. So why I'm using this padding is in order to utilize all the values which is available in the image. Because as you see in this particular example, when I set a stride value of 2, there are no more columns in the further to move, right? So that I can avoid that particular scenario by using something called as padding. Okay. So a kernel can be visualized, like a neural network with the weights assigned like this. So finally, what we are trying to do here in the CNN is we are trying to learn the values for this weights, during the training process. Okay, so that is what our ultimate problem is. So this is how an architecture of a CNN will look like. Okay, for the same example which we have taken earlier, that is American Sign Language. Okay, so this is a 28x28 image. So one is nothing but this is a grayscale image. Okay, not a color image. If it is a color image, it will have 3 channels RGB. But in our example, it is a single gray channel. So that is 28x28x1. So we can, give 2 kernels and convolve it so that we can get a 2 stacked images, okay, of this particular original image. And finally, I, expose that particular image to another set of kernels like this. Okay, then I can get again a stacked image like this. Okay, so you can have so many layers like this in CNN. Okay, there is no defined number of, convolutional layer or something like that. Okay, you can have any number of layers which works best for your model. And finally, what we do is, finally we just flatten, right, the feature vector, whatever we get here, and then we add 2 dense layers followed by the output layer. So in this output layer, as you can see, for the American Sign Language example, we will have 24 classes here. That is 24 number of, the output neurons at this particular output layer. That is 24. Okay. So this is what, an overall architecture of a CNN will look like. Okay. In the next example, which we are going to see, we are going to develop a CNN, okay, similar to this particular architecture. In an earlier example, we have seen a simple, neural network, right? So in this next example, we are going to take the same American Sign Language data set and see how, CNN can be used, for the prediction, and we will see how the training and validation accuracy are. Because in our earlier example, we saw that there is some level of overfitting, right? So we see whether CNN can be used to avoid that. Okay. So yeah, this particular slide says there are this is a kernel which is used for vertical edge detection, and this kernel can be used to obtain the original image, and this kernel for finding the horizontal edges. So there are some predefined kernels like this which we can use for our the image processing applications. Okay. So now, this is what we have been talking about. So we have an input, layer followed by different convolutional layers, and finally we have 2 dense layers followed by the output layer, which is corresponds to similar kind of architecture which is shown in this particular slide. Okay. So how an convolutional neural network works is, in the earlier layers we are able to learn the generalized features, and when we move towards the end of the our layers, we will be able to learn more specific features. So that is what we have to understand, right? So that is what also has been given in this slide. So in the in the first few layers, we will be able to first detect the edges, then we will learn the textures, then finally we move on to identify the objects which is available. Okay, so we just move from generalized feature learning to the specified features which is available in the image. And there is something called as max pooling in CNN. Max pooling is nothing but it is going to take a maximum value of this particular window which we set here. So this is nothing but downsizing the image. Okay, the max pooling is used to basically downsize the image, as you can see here. And there is something called as dropout also. So dropout is nothing but randomly I'm just dropping few neurons from the learning process, so that I just wanted to have an unbiased learning. That's what. Okay, so if I set a dropping rate to 0, all the neurons participate in the learning process. If it is 0.2, randomly I just switch off two neurons, and this is for 0.4. Okay, so dropout is mainly used for avoiding certain number of neurons randomly for participating, so that we can have a unbiased learning. That is what it is. So this is what a whole architecture might look like. Okay, so this is there is not defined an architecture. There should be only these many convolutional layers, and these should be there, and that should be only these two max pooling layers or nothing. Okay, whatever works best for you, you can trial and error. You can study those layers. Okay, generally a whole architecture might look something which is given in this particular slide. We generally represent a CNN in a horizontal way in order to save space, right? So we have an input layer followed by convolutional max pooling. Again, we have one convolutional layer, dropout layer, max pooling. And finally, we have two dense layers and output layer. Okay, fine. So we try to see another example, which we are going to apply to the same problem of American Sign Language by using CNNs. Okay. Sorry, I'll just open my American Sign Language notebook for CNNs. Okay. Okay. So let me explain this. So this is the same data set which we have taken from the Kaggle, that is American Sign Language. We have 24 classes. Now we are going to build a convolutional neural network. Okay. Let me tell you what is the difference here. Okay, the same thing. We are just reading the training data and validation data. And these are the same thing which we have seen in our earlier example. We have split our data set into training and validation, and we have stored our images and the corresponding labels in X-train, Y-train, X-valid, and Y-valid. Okay, and the number of classes is assigned to 24, and then we have normalized our image because the values of pixel will range from 0 to 55. So we just normalized it, and we are just reshaping it to fit into 28 cross 28 into 1. Okay, so if you see the shape of the training data, so it is still the number is 27455. The shape is what? 28 cross 28, and the number of channels is 1. Okay, similarly for validation also, the pictures, the size is 28 cross 28 into 1. The number of samples is 7172. Okay, fine. So these are all the same. So the difference comes here, right? So see here. So from the Keras, okay, so we have to import the following libraries in order to develop a convolutional neural network. So it is almost similar to the previous example where we added a dense layer, right? So here we are just going to add a convolutional layer. So I just create a base model, which is a sequential model. So sequential model is what? It will be, I'll be able to stack multiple layers, right? So first I create a convolutional layer and a batch normalization layer. So what is a batch normalization is, right? Whenever I, divide my data set into different batches, so these data will have different distributions. So these, batches will have different distributions, okay? So that, my learning will also be affected by the distribution of data. So in order to make, the learning independent of this distribution, we are going to do something called as batch normalization. So that is what is called as, it is again a kind of normalization only, which we call as a batch normalization. So this is a batch normalization layer. Again, we have a max pooling layer, convolutional layer, and a dropout, and so on. And finally, if you see, okay, finally we are just having a flattening layer followed by two dense layers and a final output layer. So output layer is what? The number of classes is 24, and again it is going to use a softmax layer. Okay. So if you see the parameters it is going to take you, right? So we have 27 different 75 number of neurons, and the kernel size is 3 cross 3, and the stride value is set to 1, and the padding is set to same. Same means, the original size of the image will be retained. Okay. And the activation is renew, and the input shape is 28 cross 28 into 1. Okay, so this is almost, the parameters are almost the same across all the layers. Okay, so if I, so that is what is meant by the explanation of these layers are given over here. What is meant by convolution and batch normalization, max pooling, dropout, which we have seen in the slides. Okay, so if I see the summary of the model, similar to if I call some model.summary, it will output like this. Okay, so for each and every layer I have added, what is the number of parameters? Okay, so the number of parameters is what? Number of parameters the model has to learn. Okay, so for the convolutional and batch learning, there is some parameter which it has to learn. For max pooling, there is no parameter to learn. Max pooling and dropout layers are so on. That is why it is given as 0. Okay. Finally, these are nothing but the number of total parameters the model has to learn. Okay, so the output size is what? 24. 24 corresponds to the number of classes A, B, C, and so on. Okay. Again, the same thing. I just compile my model by calling the compile, by setting the categorical class entropy. Again, I'm going to study the accuracy. Okay, so my model is training now. Okay, so once my model has completed training, we have to see how our training accuracy is and validation accuracy. Okay, let's wait for some time. There is a formula to calculate the number of parameters here. If you want, I can share this to you. So meanwhile, my model is training. Let me explain the parameter calculation. So for a simple neural network, the number of parameters will be input shape into output shape plus number of bias. Okay. So for each and every neuron will have one bias. Okay. So if I have 75 neurons, number of bias will be 75. So this will be the parameter calculation for a simple neural network. That means in our previous example, we used a simple neural network, right? So for that, the parameter calculation formula is this. And for a CNN, this is the parameter calculation formula. Okay, so CNN is nothing but the example which we are using currently. Okay, M cross N is nothing but the size of the filter. So here we have 3 cross 3 filter, right? And the D is the number of filters. Okay, and in the previous layer, and K is the size filter, number of filter in the current layer. Okay, so using this formula, you can apply and you can arrive at you can understand how the number of parameters are calculated. Okay. Okay, it's a bit slow. Okay, so it's 12:03. Dr. Meghala, still how more minutes are left for us?
Actually, we have to wind up by 12 o'clock, ma'am.
Okay, fine. So meanwhile, my model is training. I'll just conclude my last part. Okay, we are about to finish. Okay. So last part is pre-trained model. So you need not create all layers like this, which we have seen in our example. There are pre-trained models which are already created, tested, and given to us. We can readily make use of that pre-trained models. So these pre-trained models are available in the TensorFlow Hub, Keras, and PyTorch, and also NVIDIA NGC also has these kinds of pre-trained models. Okay, so your VGG net, right? So VGG16 and VGG19. So these are popular, pre-trained models. So VGG has, won this competition, the ImageNet competition. So, and in this particular slide, I have given these are the number of pre-trained, many pre-trained models which is available in KRS, like your ExceptionNet, VGG, ResNet. So, the models can be readily, downloaded, and you can just pass the data and you can get the classification output. Okay, you need not add layers. Already the layers are added and it's inbuilt in given page. Okay. So this is a summary. We have concluded, we have come to the end. We have seen what is a neural network and how a simple model works and how a convolutional neural network works and how to validate a model by using accuracy and what is a pre-trained model. Okay. So that's all about my presentation. I'm just waiting for my model to execute. It is a bit slow, but as you can see so far, the training the training and the validation accuracy will also try to improve when compared to the previous example, so that the CNN will be best suitable for image classification problems like this. So that is what the conclusion which we can arrive. Okay, so I think we can stop here. And is there any questions? I can take it up.
Participants, is there any doubts? Do you have any queries?
Okay, is there something in the chat?
We have unmuted the participants. Is there any query? Yeah.
Okay. Thank you, participants, for giving.
Hello, ma'am. How are you? Madam,
Yeah,
madam, good evening, madam.
Good afternoon, sir.
Madam, sorry, madam. Madam, how can I prove the novelty in deep learning model, ma'am? Any suggestion, madam?
See, you can prove the novelty in any deep learning model by using the metrics only, sir. So here we have, studied an accuracy metric. So there are also other metrics which you can include. Say for example, you can, you try to improve the accuracy. Say for example, if you have a base model, you just try to calculate the accuracy value, and for your model, say for example, you have modified it or altered some more layers to that. If your accuracy value is improved, then there is a novelty in your model. So in the last slide, which I showed, a lot of pre-trained models. So what is the basic thing that they are doing in the pre-trained model is they are trying to improve this accuracy by suggesting different, architectures. That's it.
Okay, ma'am.
Yeah, you can explore the KRS library and what kind of metrics you can use, and you will be able to prove some kind of improvement in that.
Yes, ma'am.
You can prove.
Yeah, ma'am, in general, if we are applying some papers, conference or some other thing, they are telling there is no novelty in the paper like that, ma'am.
Okay, okay. See, novelty is, some kind of value addition they are trying to, see from your work, right? So say, for example, the problem statement which you have chosen is not addressed by any of the researchers. You can bring in some kind of novelty in selection of the problem statement. That is the first step. And the application of the solution, application of the technique, that you have chosen. Say, for example, the people are still using VGG, 16 or 19 or something. You are trying to propose VGG 256. You are just trying to increase the depth of the layer and you are adding some more parameters, or you're trying to optimize the parameters. There also some novelty comes in, right? So the novelty is in different stages of the research. It starts from the selection of the problem statement.
Yes. Okay, ma'am. Okay, fine, ma'am. Thank you, ma'am.
Thank you.
Very informative session, ma'am. Thank you.
Thank you, sir. Thank you, sir.
Thank you. Hello, ma'am. Hello, ma'am. How are you?
Yeah, I am fine, sir. How are you?
Fine. Thank you so much for the power and the fruitful presentation, ma'am.
Thank you.
Yeah, but it will be very useful so much if you can share with us the Jupyter notebook that you have applied for revision.
Okay. Yeah, sure. I'll do that with the coordinator. I think coordinator will be able to communicate those to you. Right?
Thank you so much, ma'am.
Thank you. Thank you. Thanks so much.
Any other queries, participants?
I don't think any questions is in the chat. If there is any question, Dr. Meghla, I think you can help me out.
No questions in the chat box, ma'am.
Okay, fine.
Irka. Yeah, ma'am. One question is there, ma'am.
Yeah. What is the question?
Only image classification will get better results in CNN. What about statistical data set? This is the question available in the
Statistical data set, you mean the regression model you're talking about? The CNNs, basically work for images. Okay, so that is the main purpose of, CNNs. If I wanted to work for textual, the text kind of data, I can use, the RNNs and or what to say, the LSTMs are popularly used. That is for, the natural language and those kind of applications. I can use RNNs and LSTMs and the transformers and so on. And this CNN will be mainly used for the image, kind of data set.
Thank you, Vimla ma'am. Can you stay back us with for the feedback? Can I get feedback from the participants for all the 5 sessions? Can anyone give us the feedback?
Hello.
Yes,
Hello.
sir. You're audible, sir.
Yeah,
Yes,
this
sir,
is
you're
Dr.
audible, sir.
Yeah, this is Dr. J. Murugan,
Yes, sir.
Professor, Department of Computer Science Engineering, Savida School of Engineering, ma'am, Savida University, Chennai.
Yes, sir. Hello, how are you?
Yeah, I attend all the sessions, ma'am. It was very good, ma'am. Actually, really, we are enjoyed all the FDP sessions. And would like to special thanks to our FDP organizer, Dr. Prem Kumar sir and Meghala ma'am, Associate Professor, for the Department of Computer Science and Manakula Vinayagar College of Engineering, Pondicherry. All the resource persons are really knowledgeable persons who explained the current industrial application space. Actually, the session is also very good. I special thanks to Dr. Vimala ma'am.
Thank you, Dr.
This FTP session is really very informative, ma'am. As well as they're going to take a better view of this one.
Okay, thank you.
Yeah, thank you, ma'am. Thank you, ma'am.
Thank you, Dr. Vel Murugan, sir. Thank you for your feedback.
Thank you, ma'am. Thank you.
Is there any other participants who wish to give the feedback?
Okay.
Hello.
Thank you all. Yes, sir.
Yes, sir.
This is Siddharam, HOD Jain College, Bangalore.
Hello, sir.
Can you hear me?
Yes, sir. Yes, sir. We can hear
you, sir.
Yeah, it is very informative session. Thanks to all organizers. And 5 days, we gained a lot of knowledge of this FDP. And we are expecting in future also, please organize some other topic like deep learning and image processing. Madam?
Yes,
thank you, one
sir.
and all the organizing committee.
Thank you, sir.
Thank you.
Thank you, Sitaraman, sir, and thank you for the wishes. And definitely, we'll be organizing such FTP programs in future with very different platforms and technologies. Thank you so much, sir. Thank you for the.
Thank you.
Okay, Meghala, is it the last day of the session?
Yes, ma'am. Yes, we have invited you for the last session. It's a very interesting session.
Okay, thank you. And participants, I'm just sharing my mail ID here in the chat. If there is any queries or you can drop me a mail, I'll just reply. If not in 24 hours, I'll try to reply for that.
Yes,
Vimla ma'am.
Yeah.
Dr. Vimla ma'am, it was a very informative session. Thank you so much for sparing your time, because I told you in a very short time span, yet you made it a very special day. So thank you so much. And
because because SMEC is special to me, so I wanted to make it special.
Yes, ma'am. We are proud to see you. Great alumni for us. Thank you. And we'll wind up the session with the vote of thanks, ma'am.
Yeah.
A very happy afternoon to all. It's my great privilege to deliver the vote of thanks. And ignited mind is the most powerful weapon on earth, above the earth and under the earth. And this is got through continuous education. I thank Dr. M. Vimla Devi ma'am for igniting the minds of participants with a very informative session. And I also thank all the speakers of this FTP Mr. Khadar Nawaz of VIT, Dr. Nalini, Mrs. Ponmalar, and Dr. Prasad. It's my bounden duty to thank our management and Director cum Principal, Dr. VSK Venkatachalapati, for encouraging us to conduct this FDP. And I also thank our HOD, Dr. K. Prem Kumar, for his continuous support in conducting this FDP. And also my special thanks to all my colleagues for their immense support and encouragement. And I also thank all the participants for the participation and making this FDP a great success. Thank you all. And you will be getting the certificates within 1 week of time span. If you have any clarifications or queries, kindly mail to us. And we have given our mail ID in the browsers. And you can also connect to our WhatsApp group. Vimla ma'am, thank you so much, Vimla ma'am.
Thank you. Thanks a lot for inviting. I'm just winding up. Bye-bye.
Yeah, ma'am. We'll end up the session.
Yeah.
And feedback will be sent in the chat box, and participants are requested to fill the feedback within 30 minutes of time span. Thank you all.